Hello. This is an introductory discussion for Unit 4, Transformations and Similarity. In particular, I want to go over and explain what similarity means from a geometric perspective. In this section, similarity is going to come up and be referenced in some of the more difficult assignments in this unit. Similarity has a very specific definition we need to use in geometry, so let's go over it. So let's start by looking at these two triangles. Just visually looking at them, they do seem similar. We have a longer side, a shorter side, and we have sides that are opposite what seems to be a 90-degree angle. So just visually looking at them, we could say, yeah, they seem similar. But that's not enough to call them similar when we're looking at it from a geometric perspective, when we're doing geometric work on these two triangles. So let's go ahead and look at the given definition of similarity. So the definition you're given is similar figures are those with congruent corresponding angles and proportional sides. Under a dilation, the image will be similar to the pre-image. So that's a very good definition, a very comprehensive definition, but it's not the most clear. So let's go ahead and show you what that means on a practical level. So in order for me to check or prove if these triangles are similar from a geometric perspective using geometry, I need to check two things. I need to check and see if they have equal angles and the sides are proportional to one another. So the first part is easy enough. I choose my measure tool and I reveal the angle measures at both triangles. I have to zoom in a bit to check this one. We have 90, 63.43, 27.57, 26.57, excuse me. And we have 90, 63.43, and 26.57. So, yes, they do have equal angles to one another. So, that part is confirmed. So, we're on our way to proving that they are similar. The angle part is taken care of. But now we need to check whether or not the sides are proportional, and I'll go over that right now. So, I'm going to start with the long side on each of these triangles. So AB is 4 units long, and DE is, no, I don't want the perimeter, 2 units long. ED is 2 units long. So the two sides, just comparing them, it looks like the smaller triangle, or at least the smaller side of ED, is half the length of the bigger triangle AB, or the longer side of the larger triangle AB. So right now I'm just comparing two sides, but now I need to check and see if that holds true for the rest of the sides. So does BC have twice the length as EF? Yes, it does. 1 is half of 2, so the proportion holds right now. And lastly, AC is 4.47, and we have 2.24. And with a touch of rounding, we could say confidently that yes, they are proportional to one another. So all the sides of ABC are proportional to all the sides of EDF. So we can then conclude that they are similar. So using our geometric definitions, we have proved that triangle ABC and triangle DEF are similar. So let's go ahead and try another set of triangles. So let's compare ABC to GH. Yeah, GHI. So let's go ahead and first measure their angles. So we have our angles there, and here we have a bit of a problem. So 90 and 90, those are still equal to one another. But here we have angle C to be 63.43 and angle I to be 68.2. Well, maybe we'll have better luck comparing angle C to angle G, but no, that's 21.8. So the triangles are not similar because the angles are not equal to one another. And we could double verify by checking out the distance or the length of AB compared to that of HG. So we have a ratio of 4 to 5, but BC is equal to HI. So the proportion does not hold for all angles. We have one side that's equal and one side that is not equal, and that has a ratio of 4 to 5. So even though if we look at them, we could say, yeah, they're similar, just not using the geometric definition. We have the long side, the short side, the hypotenuse, long side, short side, hypotenuse. But using our geometric definition, these are not similar. So when you encounter situations like these where the angles are not similar or the sides are not proportional, you're going to conclude that those triangles are not similar to one another. So this definition of similarity holds true for all sorts of different shapes in geometry. If you have a rectangle, or if we're comparing two rectangles, you could check for similarity by checking to see if their angles are equal and checking if their sides are proportional. If either one of those fails, then they are not similar. So that works with rectangles, pentagons, hexagons. It works for most any shape that you're going to work on in geometry. So keep that definition in mind. Remember those tests, and good luck with the rest of your unit.